Hello, class. This is Mr. Hart, and in this podcast, we want to finish up the earthquakes chapter of our textbook. And today, we want to be talking about how we actually measure earthquakes and prepare for earthquakes. So, you probably have seen before some of these wave outputs that earthquakes generate, from the shaking and all the movement. We can kind of see how much the earth is displacing itself or moving back and forth. And if you look, we can actually see two distinct peaks or two distinct locations of where there's lots of movement. Okay, so at one time you can see this peak right here, which is most likely associated with the P wave because it arrives first. And then at this peak over here, it is most likely associated with the S wave, so it arrives second. So at some station that's measuring earthquakes, we can see the arrival of these two waves from the earthquake. And so we want to go more into how we actually determine how large of an earthquake we have, how far away the earthquake is, and so we want to look at some of these ideas. Okay, but the first thing we need to do is we need to look at some vocabulary. So these machines that actually look at these wave outputs we call seismographs. Okay, and that's just a machine that kind of determines how much the Earth is actually moving. Okay, and then how we determine how large an earthquake is, we use the Richter scale. You probably heard this before, but the Richter scale is just a measurement of the magnitude of an earthquake. Okay, so seismograph is the actual machine. The Richter scale is how we determine how big it is. Okay. So if you've ever seen a seismograph, you've probably seen this little needle that sticks out and is on a piece of paper, and it moves back and forth, and it moves left to right, and it generates the wave outputs that you can see. So how it works is this roll of paper is just slowly rotating, okay, slowly rotating down, and as it goes down, the needle is just resting on top of it. And so as the earthquake moves the earth back and forth, the needle will move left and right as the earth underneath it is shifting. Okay, so there's a complex set of gears inside this needle that kind of amplify this movement. If you've ever seen a seismograph needle, it moves very quickly. That's not how fast the Earth's actually moving, but it's an amplification of the movement. And so this needle is kind of isolated from the rest of the machine. You can imagine that if you had this drawn out, a lot of people say, oh, here's the seismograph, here's the needle coming down, and the needle's moving back and forth. That's not the case. Actually, in reality, the Earth's moving back and forth, and the needle and the system are isolated. So they're just sitting there, and they're writing down what's happening, but in reality, the Earth is shifting back and forth underneath it. Okay. And again, this isn't the exact same amount of movement because this system is amplified. They have a specific set of gears to help it move more so they can see what's happening. But in the simplified version, what's happening is the needle is sitting there, and the Earth's moving back and forth underneath it. So you get these wave outputs, these lines that are going back and forth. Okay, and so it kind of works like a typewriter. As it goes through the paper, once it gets to a certain part where it no longer has any paper to work with, it'll move the machine down. It'll start recording down here, and then it will move the machine down again. It'll start recording right here, and so on. And then you would replace the paper, replace the roll with a new sheet. And so this is kind of the very basic layout of a seismograph. Obviously, you can get much more advanced equipment, much more electronically enabled equipment. And so, but this is just the general layout. And so what they do is after they get that measurement from the seismograph, they look at the distance these lines went on the paper, and based on how far those moved, they give it a Richter scale assignment. Okay. And how the Richter scale works is it's a log scale, meaning it multiplies itself as you go up. So an increase by 1 on the Richter scale means there's 10 times the energy. So if I'm a 6 on the Richter scale and I move to a 7 on the Richter scale, there's 10 times more energy from a 6 to a 7. If I go one more up from a 6 to an 8, that's 100 times more. So you can imagine a good way to think about it is every time I move up a number, for example, a 6 to an 8, okay, there's a difference of 2 between a 6 and an 8. So I'm going to have 2 zeros on the end of my numbers. So there's 100 times more energy. If I went from a 4 to a 9, that's a difference of 5. So it's going to be 1, 0, 0, 0, 0, 0. I'm going to have 5 zeros, which means there's 100,000 times more energy. Okay, so don't get deceived. It may sound like a 7 compared to an 8 is not that big of a difference, but it's 10 times more energy on the Richter scale. Okay, so a 5 earthquake is about when we start to feel it. Okay, if you feel an earthquake actually shaking your house, it has to be at least a 5, generally speaking. Okay, 6 is when you start to see a little bit of damage. 7 is really a strong earthquake, would start to destroy some buildings, start to destroy some facilities and things like that. You might even have some fatalities. Okay. 8 is a, very deadly earthquake. That's where you start to have, some great devastation. And a lot of the reported earthquakes you see on the news would be an 8 scale. Very rarely will you get a 9, but 9s are very, very large earthquakes, kind of the super earthquakes. Okay, so if you see anything between a 7 and a 9, generally that's a very big earthquake that would probably get reported on the news. Okay, these ones down here you probably won't even feel them if you have a 0 or a 1 or a 2. You won't even notice them, but you can have these different levels of earthquakes. So just remember, every time you move up 1 on the Richter scale, you are timesing by 10 in the amount of energy. Okay. So once those seismographs actually get a reading of how strong the earthquake is, then they have to find its position by using triangulating, okay, or by triangulating the epicenter. And so what happens is, let's say you have the seismograph in Portland and it measures a 4 on the Richter scale, and the one in Salt Lake City measures a 5, and the one in San Francisco measures a 6, okay? Well, all these scales are getting different numbers, but that's a good thing. It means the epicenter isn't exactly in that location. We can use what's called triangulating. Okay, so this one had a very weak earthquake, so they know that the earthquake has to be somewhere in this radius. This one had a slightly stronger one, so it might say that it was in this radius. And this one had a very strong one, so it has to be much closer. So each seismograph has a certain radius where the earthquake could be, and based on the different seismographs, then you can locate exactly where the epicenter had to be. Notice that it lines up with this epicenter, lines up with this seismograph, it lines up with this seismograph, and it lines up with this seismograph. Okay, you need to have at least 3 seismographs in order to find the epicenter. Because if you just had one, for example, if you just draw a circle, okay, that's one epicenter. Okay, notice you can't really determine where it could be because it could be anywhere within this distance. If you just have 2, okay, actually let me draw it like this. If you just have 2, then it's better, but you still can't exactly triangulate it because you're going to have 2 locations where the epicenter could be. It could be right here, or it could be right here. Okay, so in order to get an exact position, you need to have at least 3 seismographs, like it is shown here. Okay, that's the only way to get the exact position. You can get an approximate with 2 or 1, but in order to get the exact location, you need at least 3. Okay, and so that's what they do. So they get the seismograph, it measures the Richter scale. They use that information with other seismographs to determine where the epicenter had to be located. Okay? All right. So that's the process, okay? Take the seismograph, find the Richter scale measurement, use that to determine the location of the earthquake. So let's look at how many earthquakes we actually see in a year, okay? So it might be surprising to hear this, but in a single year, more than 900,000 earthquakes are recorded, okay? That's a lot. If you do the math, that's like 300 every day or something, or even more than that. No, maybe it's 3,000 every day. It's about 3,000 every day. So it's quite crazy to think about how many earthquakes are happening. Okay, 150,000 of them are strong enough to be felt. But keep in mind, some of these happen in the ocean. Some of these happen in uninhabited areas. A lot of them you won't feel. So it's not like these are happening every day and people are feeling these earthquakes. A lot of them are in areas that are uninhabited and areas that, it's not any big deal that an earthquake's happening. Okay. Only about 18 earthquakes are major every year. Okay. And there's often about 1 earthquake that has a very large magnitude that does a lot of damage. Okay. So just keep in mind there's lots and lots of earthquakes that occur, but only a couple dozen are actually ones that would be something that you would report or see on the news. Okay. This one is an example of a magnitude 9 earthquake, or a believed magnitude 9 earthquake. You don't see these every day, obviously, but this is a picture of what the damage looked like. You can just see how this whole street just sunk into the ground. Okay, but so about around 20 a year would be something you would actually report, but there's tons and tons of earthquakes happening every day. We just don't notice them. Okay. All right, let's talk about one more idea with earthquakes, and that's liquefaction. I don't know if that's how it's pronounced, but it's the only way I can figure out how to say it right. But liquefaction is the process where the soil underneath the structure or in the foundation is not settled properly, And so when an earthquake occurs, it'll actually start to act like quicksand and will sink the entire side of the building down into the ground, like it's shown here. Okay. If you think of the Leaning Tower of Pisa, you can think of that where the soil was not very settled. And so it has slowly over time started to lean, right, has sunk into the ground. Okay, but this is a very big problem with earthquakes because it kind of magnifies this process and speeds it up. So if you've ever had someone in construction or in architecture and they've tried to start building a building, you'll hear that they have to do a soil test. And this isn't because they're trying to plant anything in the ground there, but it's because they want to make sure the foundation will not have this problem of liquefaction. They want to make sure it's nice and firm. It's not going to sink and turn into quicksand after they build the building. Okay. And so, especially with earthquakes, this is a big deal. As we've gotten to understand this process more, we're doing more things like soil tests before we build buildings. We're making sure the foundation is nice and sturdy so that we don't have this problem of sinking buildings, especially during an earthquake. Okay? All right. And so that's all we want to talk about with that part of the chapter with actually analyzing earthquakes. The last thing we want to look at is earthquake safety. So you probably have learned since you were a kid at school that when an earthquake occurs, you get under your desk, you hold on tight, and you cover your head. Okay, but let's talk about some of the other things you can do, not just at school, but when you're at home and in other locations. Okay, so there's three things or three different parts to this. There's the before, the during, and the after the earthquake. Okay, so some of the things you can do before the earthquake are to be sure that heavy objects are not stored in high places. Hopefully that makes sense. You don't want anything to fall on you. Secure your water heater all around at the top and the bottom. You don't want your water heater to tip over, not only because it'll have tons of hot water that can burn and damage equipment and people, but it also has a pilot light in there, right? It has the gas line connected to it to actually heat the water. So if that gas line breaks, that could be very bad. That can cause a fire or some type of explosion. Okay. Bolt heavy furniture onto the walls with bolt screws and strap hinges. Especially the bookshelves and things like that, things that will easily tip over. You generally want to put a screw at the top so it does not tip. Replace halogen or incandescent light bulbs with fluorescent light bulbs to lessen fire risk. Hopefully you've already started to do that as the incandescent light bulbs have kind of been phased out. Have an earthquake kit ready with 3 days of water and food, a radio and batteries, just general emergency supplies. Have flashlights all over the house and in glove box of your car. This is less of a problem as well, as people have cell phones now, and a lot of their cell phones have flashlights. But if your cell phone breaks, you want to make sure you have some backups. Keep fire extinguishers around the house. Have a first aid kit ready to go. Okay, so some general, just any type of emergency, you want to have these things ready to go. Okay, during the earthquake, some things you probably want to do are, if you're in a building, get beneath the study table, cover your head, and hold on. This is probably something you've learned. But here's some other ideas. Stay away from windows, mirrors, and large furniture. Anything that will tip over, anything that could shatter. You don't want to be near those things. If in a building is structured unsound, get outside as fast as possible. Generally speaking, it's hard to tell if this building's unsound, but if you have a feeling that it's going to go down, then you want to get outside. If you are outside, run to an open area away from buildings and power lines that may fall. Again, if you're in an open field during an earthquake, you are completely safe because there's nothing that can fall on you. Generally speaking, it's the things that we have built as humans that can cause the most damage. Okay, if you're just in an open field, an earthquake can't do anything to you. If you're in a car, stay in the car and stay away from structures that might collapse, such as overpasses, bridges, or buildings. Okay, don't try to leave your car. It's generally safer just to stay inside as long as you're away from things, and just wait out the earthquake. After the earthquake, just be aware that aftershocks are likely. You don't want to, celebrate too early. Stay in your car or stay in the building. Just wait. Make sure nothing else is coming. Avoid areas that may experience a landslide. Okay, if you're on a hill, get away from that. Turn off water and power to your home. This one's a big one, and people often forget to do this. Is if an earthquake occurs, it generally has caused some type of damage in your plumbing or in your power lines, and you want to turn off the power and the water until you can be sure that there's no leaks or breaks or anything like that. Okay, a lot of times people leave those on and then they don't realize they have a problem in their house, and so when they turn the power back on after a while, there's been sorry about that. After a while, they turn on the power, or they're trying to turn something on, then there's a break in the line or there's something like that, and it's causing a huge leak, or it's causing flooding, or it starts a fire because there's a break in a wire or something like that. So you want to make sure you turn it off until you're sure that there's no damage that's been done. Okay. Here's another big one. Use your phone only if there is an emergency. Many people are trying to get through to emergency services. Okay. So if you're okay, if you're safe, there's no instant problem that you need to deal with, or immediate problem that you need to deal with, don't call 911. Okay. Everyone's going to be trying to call 911. Their lines are going to be super busy. Don't call them unless you have a very immediate emergency that you need to deal with. Okay. If you're fine, if there's some damage, but it's not something you need to deal with right away, then wait an hour, wait a few hours, make sure that they deal with the right away emergencies, the immediate emergencies first. Okay. And then be prepared to wait for help or instructions and assist others as necessary. If you're in a public area, for example, be ready to assist others, or listen to an administrator that may need you to do something. Okay. All right. So that is it for this chapter. Hopefully that all makes sense. Let me know if you have any questions, and thank you for watching.